So this is a lecture on determining the deflection and slope in a determinate structure, and specifically we'll see on the beam using the unit load method. And for calculating the deflection we'll use this equation, integration 0 to L capital M small m upon EI into dx. How we got this equation? We have to equate the Wi with We, internal work done equate to external work done. So when we equate these two, we get delta is equal to integration 0 to L mm dx upon EI, and this equation we'll use for calculating the slope. So these are the two equations which we have to use, and we have to familiarize ourselves with the terms which are given here. In this there are two terms, capital M and small m. Capital M is the bending moment of the real expression, real structure, as a function of horizontal distance x. Since we are integrating everything with respect to x, the bending moment equation will be formed as a function of horizontal distance x. And if we are using the real structure, means the structure that is given in the numerical, we'll call it as capital M. And suppose we are using the virtual structure, we'll call it as small m. How we create a virtual structure? By simply removing all the loads of the beam and applying a unit load on the beam, right, and forming the similar equation with a horizontal distance x. And this is for deflection. Suppose we want to calculate the slope, what we have to do, instead of applying unit load, we'll apply unit moment. So always remember that when we calculate deflection in a beam, we'll apply unit load, unit point load at the point where we want to find the displacement. And suppose we are interested in calculating slope, what we do, we'll apply a unit moment in the virtual structure. We'll see it is a very simple problem. So this is the first problem. It is a simply supported beam with a central point load. So we want to calculate maximum deflection. So maximum deflection will be under point load only, since this is a symmetrically loaded. Deflection under the point load or deflection at the mid span. So all the things are same only. Actually we have to calculate deflection at C. To calculate the reaction, how to calculate reaction? By using equations of equilibrium. Since the structure, as we can see, it is symmetrical, and both the supports will share the load equally. So what is the total load? Total load is capital W. So reactions would be half of that, that is W by 2. Table we have to use for calculating this deflection or slope. So actually it is rewritten in this form only. It is delta, that is deflection at point C, is equal to integration 0 to L capital M small m dx upon EI. So how we write all these things? We split up it in a form of table. So first is portion EI, that is modulus of elasticity and moment of inertia. Origin, limit, capital M and small m. We'll see what is this. So portion, we see that this is a beam having a point load in at point C. So portion is, as per strain energy, is where the bending moment equation does not change. And whenever there is a point load or a UDL starting or finishing, there will be change in the bending moment expression. So we'll call it as a portion. Portion we define as, portion is a part of a beam or a region in the beam where bending moment equation does not change. Suppose what we do, we consider portion AC, and we consider section this. We'll find that bending moment equation is RA into X. And similarly, if we cross this line, cross the point load, what we find that now the bending moment expression is changing. So we understand that now we have to split the entire beam into two parts, that is portion AC and BC. E is the modulus of elasticity and I is the moment of inertia. Together they are known as EI, together they are called as flexural rigidity. And very well we can see from here that delta is inversely proportional to EI. Suppose if we want to reduce the value of deflection or you want to increase the rigidity, what you will do, you will increase the value of EI. And generally we don't change the material because E is the material property, so we don't change it. We change the cross section of the member origin. What we know that when we form a bending moment equation, it can be formed from the either side of the section. Suppose I consider portion AC. Now either I can form the bending moment equation from left hand side, or I can make the same equation from the right hand side. What we generally do, we'll see that wherever the number of forces are less, we go from that side. So for the portion AC, what we do, we'll consider the left hand side equilibrium of the section. So what will be the origin for the portion AC now? We are starting it from A. So this distance now will be measured from A. So origin for portion AC will be A. Similarly, if we see for the portion BC, for this portion BC, now we are standing here at section. We see that there are two forces here. One is point load, the other one is reaction. So instead of calculating from the left hand side, we'll calculate the bending moment equation from right hand side. It will be very simple. So what we do, we measure this distance x from point B. So now for the portion BC, the origin will be B and bending moment equation will be force into distance. And you see that we have to integrate everything from 0 to L. So what we do, limit is the length of the portion. Suppose we are considering portion AC. What is the length? It is L by 2. So limit we will write 0 to L by 2. And for BC again the length is L by 2. So now we will split this structure into two parts. First one is the real structure, the other one is the virtual system. And we have to use this expression, right? So what we do with the real system, we calculate the value of capital M. Real structure means the problem that is given in our question. How we create a virtual system? Simply remove all the loads and apply a unit load at the point where deflection is required. So now this is our real system and this is our virtual system. So in this system we find that there are two portions. First portion is AC, the other portion is BC. So portion is AC, BC. What is the value of EI? No change in value of EI is given, so we will consider it to be constant, EI. So now for the portion AC, we should consider left side or right side. So yes, we will calculate the consider the equilibrium from the left hand side of the section. So the origin should be at A. Similarly, for preparing bending moment expression for portion BC, we will consider the right hand side of the equilibrium. So origin will start from B. So origin will be at B. What is the length of the region? For AC, the length is L by 2. For BC also it is L by 2. So we will write limit as 0 to L by 2. Now we want to calculate the bending moment, capital N, in terms of X. So we are standing here and this is our origin. So the force is W by 2 and the distance is X. So W by 2 into X, or we can say that it is RA into X. And this is a sagging moment. Because of this load, deflected shape is of a sagging curve. So this is a positive bending moment. So we will take as RA into X. Similarly, when we solve for portion BC, we are at the section, and now we see on the other side, we find that there are two forces on the left side. So we will consider the equilibrium from the right hand side. So this distance is X. So what will be the value? It will be RB into X. So because of this load, the curvature is like this. It is sagging. So this will be positive. Now to calculate small m, we'll use this equation or this system. So for the portion AC, origin is A, load is 1 by 2 into X. So bending moment equation for portion AC will be 1 by 2 into X. Similarly for BC it will be 1 by 2 into X. So now we have written everything. In place of RA we'll write W by 2. Now we have to calculate the deflection. So we see that deflection at C will be equal to deflection in the portion AC plus deflection BC. So for AC, what is the equation? 0 to integration 0 to L capital M small m dx upon EI. So for the portion AC, limit will be 0 to L by 2. 1 upon EI is constant, we can keep it out also. What is capital M? It is Wx by 2. So capital M is Wx by 2 into small m. What is small m? It is simply x by 2. So into x by 2 into dx. For portion BC, similar terms we can find from here. This is capital M, this is small m. You integrate it and add up, you will get the value of deflection at C as WL cube upon 16 EI. We can say that deflection is downward. How we can say that deflection is downward? Because this value is positive. Positive value indicates that the direction of displacement is along the direction of the assumed direction of unit load. So what is the direction of unit load which we apply? It was downward, and this value is positive. That means it is along the direction of assumed unit load. Now come to slope. How we define slope? Slope at any section is in a deflected beam is defined as the angle in radians, the vertical angle between the tangent at the section and the original axis of the beam. So original axis of the beam is like this, horizontal. Now this is the deflected shape. If you are interested to find the slope at this point, what we do, will draw a tangent like this, and this angular displacement, angular rotation is called as slope. So this is a case of simply supported beam. So maximum slope in a case of simply supported beam will be at the support, because at midspan where the deflection is maximum, if we try to draw a tangent, we find a horizontal line only. So there is no angle between axis of the member and the tangent drawn to the point where deflection is maximum. So this is a rule we have to remember. At point where deflection is maximum, slope will be 0. This is in case of simply supported beam only. In case of cantilever beam, what happens that, suppose this is the deflected shape, and at this point we are interested to calculate the rotation. What we do, we draw a tangent. So this angle between the tangent and the original axis of the beam is called as slope. And deflection are maximum in cantilever beam at its free end. So both the things like slope and deflection both are happening at the free end in case of cantilever beam. And slope and deflection at fixed end is 0. Slope and deflection at the fixed end is 0. So now we'll use the similar problem, the previous problem, and we'll calculate the slope. So this is our beam, and we calculated the reaction. It is RA and RB. Now we want to use the two systems, that is the real system and the virtual system. Now what change we have to do is, real system remains same as it is given in the problem. To calculate slope, we should apply a unit load at a point where slope is required. Suppose we want to find slope at some point here, so this unit load should be applied at this point. As per the question, we want to find the unit load at the support. So this unit moment, it should be applied at support only. So in this case, we want to find the slope at the support, so we will put the unit moment at the support A only, right? Now we'll put everything in the table. Portion is AC, BC. What is the value of EI in the portion? What is the origin for the portion AC? For simply supported beam, we take origin as their support only. For portion AC, we take support A. For portion BC, we take support B. And what is the length of the region or length of the portion? It is L by 2. 0 to L by 2 we have to integrate. So the value of RA is W by 2. Simply we'll multiply with X. We'll get the bending moment equation. And for portion BC, again it is symmetrically loaded, so it will get the similar value. So it will be W by 2 into X. Now we'll come here that the only load in the virtual system is a unit moment. So what will be the reaction? It will be 1 upon L. It will be 1 upon L. Moment value is 1, total length is L, so it is M upon L. So what is the value? This is acting downward and this is acting upward, because the action is clockwise rotation, so reaction should produce an anti-clockwise rotation. Then only the structure will be in equilibrium. Right? So this is downward. So the value of M will be 1 by L into X from the left hand side, and for the portion BC again it will be RA into X, that is 1 by L into X. So when we solve it, we get the value W into X by 2, this portion, into X by L into X by L. For portion BC, we'll put up all these values in the equation and we will get the value WL cube upon 48 EI. Now coming to the next question, we consider a cantilever beam, which is one of the most simplest beam to understand this method. It can be solved in few lines only, right? So we'll consider this cantilever beam with a point load at its free end. We have to calculate slope and deflection. So again we will try to, this is the original structure, we call it as real structure, and this is the virtual structure we'll use for deflection, because we have put a point load. To calculate the rotation, we will put a unit moment at the place where we want to find the slope. So this one is the real structure, these two are the virtual system. Virtual system for deflection should have a unit point load at the point where deflection is required, and for virtual system for calculating slope will have a unit moment at the place where rotation or slope is to be calculated. So in the previous question, the step 1 was to calculate the support reaction, but in case of cantilever, support reactions are generally not required. As what we do, we'll take this section and consider the equilibrium on the right hand side, where we will not have the requirement for reaction. So we can skip this step. From support to free end, there will be only one bending moment equation, that will be W into X, and here the bending moment equation will be 1 into X. So these two are hogging, so it will give a negative bending moment. Okay, and what about this? This is again a hogging, so it will be a negative bending moment. We calculate moment by multiplying force into distance, so moment will be 1 into X at this point. But what about this? This is already a cooked moment, this is already a moment, so you don't have to cook it. Either you will add this moment or you will subtract this moment. So this is a hogging moment, so we'll simply write -1. What we do, portion, how many portions are there? Only one portion is there, AB. Origin will be at the free end, limit will be from length 0 to L. Bending moment equation will be capital M for the real system will be -W into X, and for virtual system, in case of deflection, for delta it will be -1 into X. For moment it will be -1, right? So we'll put up everything. Integration 0 to L 1 upon EI. What is capital M? It is -W into X. What is small m delta? It will be -1 into X. Simply integrated, it will be Wx square dx. So when we integrate x square, it will become x cube by 3. So we'll get WL cube upon 3EI. For calculating rotation we will use this capital M and this M theta. So how we get it? Minus W into X, this one, into minus 1. So when we solve, we'll get theta as WL square upon 2. So simple. Solve the cantilever beam using UDL. So again we have to use the two structures, that is real structure and the virtual structure. Then we have to create two virtual systems also. First virtual system is for deflection. As you can see, we have placed a unit load at the point where deflection is required. The second virtual system we'll use for calculating slope, because we have put a unit moment at the point where slope is required. So we'll put all the values in this table. Portion is only single portion is there. AB value of EI is constant. In case of cantilever, we use free end as the origin, and limit is the total length 0 to L. How we calculate mx? It is nothing but W into X by 2. It is a UDL. This is what is the intensity of load. Intensity is W. What is the length? It is X. So W into X, and from where the load will act? It will act from the center. So into X by 2. So directly we will write as minus Wx square by 2, because this is a hogging moment, into what is M in delta. For M in delta, it is point load at the free end, so it will be 1 into X. What is the nature? It is hogging. It is hogging moment, so it will be minus 1 into X. For M into theta, we'll have put a moment, clockwise moment, so it is already a moment, we don't have to multiply distance to it, so it will be either plus 1 or minus 1. If we closely see, the deflected shape is hogging, so this is going to be minus 1. So M theta will be minus 1. First we'll calculate the deflection delta, so we'll use these two terms only. So integration 0 to L, M into small m delta. So this will be, this value will put here, this value will put here, multiply, integrate, you will get this value, WL to power 4 upon 88. For calculating slope, we'll use this capital M and this M into theta. The value will be Wx square by 2 into 1. So minus will be plus. So we eventually get a positive value, which indicates that the deflection and rotation is along the direction of the assumed unit load. Now next problem, this is cantilever with a moment or a couple at the free end. So how we'll solve this? Again we'll split the structure into real system and virtual system. We want to calculate deflection, so we'll put deflection. For deflection we'll put a point load at the free end, and similarly we want to find the slope at the free end, so we'll put a unit moment at the free end. This will help to calculate deflection. This virtual system will help us to calculate the slope, and this is the real system. In this we find that there is a already moment is there, and what is the portion? There is only single portion, so we'll put everything here. Portion is AB, value of EI is constant, origin in cantilever is from free end, 0 to L is the length of the cantilever. So what is M? We stand here and look on the both side of the section. There is only one force, that is moment. So either this will be plus M or this will be minus M. Okay, so what we do, we'll see what is the effect. So this is bending like this, so this is a hogging shape, so we'll consider it to be minus M. To make moment, we multiply force into distance, but this is already a moment, so no need to multiply with any distance. Simply bending moment will write as minus M. And for point load, for deflection we use unit point load, so it is minus 1 into X. So multiply these two values, so put it here. So we'll get deflection at C as ml square upon 2EI. For slope, we'll use this capital M and this M into delta. M is minus M and M theta will be minus 1 only. So this is a unit moment we have already provided, and because of this the deflected shape is like this. So this is a hogging moment. So this one we will put as -1. So this one we will put as -1. When we'll solve, we'll get this theta c as ml upon ei and deflection at c as ml square upon 2ei. Now coming back to the simply supported beam again. Now this time we are considering a simply supported beam with the UDL, and we have to find the central deflection at midpoint, because this is symmetrically loaded, so maximum deflection will be at the center. So to calculate deflection at C, we should provide a point load at C. So here in the virtual system you can see that we have put a point load, and we are interested to find maximum slope also. So for a simply supported beam where deflection is maximum, slope will be 0. So slope at C will be 0. So we will try to find the slope at support. So we'll put a unit moment at support A. So how many portions are there? So two portions are there. One is AC and other is BC. In case of simply supported beam, what we do, we keep the origin as the supports. So for AC we will use origin as A, for BC we will use origin as B. What is the length of the portion? It is L by 2. So we will integrate it as 0 to L by 2. Now coming back, what we do, we take a section and this distance is X. Now this distance is X. So what is the value of RA? RA will be nothing but total load by 2. So what is the total load? W, and this total length is L. So this is the intensity of load, W. So what is the total load? It will be WL. So total load will be WL, and it will be shared equally amongst the two supports. So the reaction will be WL by 2. So what is the bending moment? WL by 2 into X minus this portion. This UDL also we have to subtract, because the effect of this reaction is sagging and effect of this UDL is hogging. So this value will keep as positive and this value will keep as negative. So the bending moment equation will be RA into X minus WX square by 2. What is RA? RA is WL by 2 into X minus WX square by 2. M into delta, M delta, this one. So what will be the value for portion AC? It will be, this is 1 by 2, 1 by 2 into X. So M into M delta will put up, and actually we see that since it is symmetrical, we will get similar values for AC and BC. So here what I have done, I have already multiplied it with 2. Single term I am considering, this multiplied by this, and everything I multiplied by 2. So eventually you should get this value, 5 WL to power 4 upon 384. Now again we will use this same table for calculating slope. So for calculating slope, capital M value is not going to change, only we have to add this value M theta. So we'll go back to our virtual system. This is our virtual system with a point moment at A, because we are interested to find theta A. So we have put a point moment at unit moment at A. So for this portion, what will be the bending moment equation? It will be RA into X. So what is the value of RA? It is 1 by L, and what will be the moment? 1 by L into X. So the M theta will be 1 by L into X. So we'll put everything. This value will put here, and this value will put here, and since the both are similar value, so we have multiplied it by 2. So eventually you should get WL cube upon 24 EI. So some of the practice problems you can solve. This is a practice problem. This is a cantilever of span 10 meters, and UDL is 12 kilonewton per meter, Value of E and I is also given, so you can solve this value and eventually you should get this answer. 10 meter is a huge span, and 150 millimeter means it is also very huge deflection is there. And one problem based on simply supported beam, so half portion is carrying a UDL of 8 kilonewton per meter, total length is 8 meter, the point load in between, so we have to calculate deflection. So value of E and I is also given in this problem, so you can cross check your answer.